All right, so we are in limits day 3. This is our third day of the semester. And as we have seen in the last week, we like to sort of start with this idea of what we know and what's new. Okay, and so the what we know list specifically gets longer and longer the deeper we get into any specific unit. Okay, so last week we talked about what is a limit. That would be an important thing that you could sort of be able to explain what a limit is. Okay. How do we find limits graphically? And so from looking at quiz 1, it looks like we've got a good chunk of the class, it looks like feeling comfortable finding limits graphically. But I think we also have some folks who are a little bit confused about what it means to find limits graphically. And that's okay, but I would hope that if you're in the confused category, that I see you in office hours or that Ethan sees you in tutoring, even though this was last week, you can still ask about it this week. That's still okay. All right, so just because it was a different week or a different day doesn't mean you can't ask for help about that particular concept, okay? Last week, we also talked a lot about how do we find limits algebraically? Like what happens if we don't have a graph? And this is where I noticed that there were a few folks who turned in quizzes, and maybe there was a situation that gave you 0 over 0, and then you just stopped. You didn't factor, you didn't use radicals, you didn't use complex fractions. And that was something that I would encourage you to go back over and try again on your own, okay? So if that was you, I would go back over and try that again, but also for sort of this chunk of content, right? So like all of this is covered on quiz 1. And after the deadline for every quiz, I do post an answer key. All right. And so the answer key I'm going to go with is ideally 95% correct 95% of the time. It does mean there are moments where I've written the wrong thing, and that is on me. So if you find like an answer and you're like, I don't think Judy's answer is right, please tell me. I would like to correct that for everyone else's sake as well. But if you're like, oh, I lost some points on quiz 1 and I'm not sure why, and I don't know how to do the questions, take a look at the quiz 1 answer key, right? And if that still doesn't make sense, come to office hours, go to tutoring, ask about those questions, reach out to a buddy on Discord, say, hey, did you get this answer to the question? Because I'm not sure what I did wrong. Okay, so lots of opportunities for us to be supported in the learning, which is sort of the ultimate goal here, right? No matter what kind of mistakes you made on quiz 1, if you learn from them, I won't see those same mistakes again on the exam, right? And I want that for you as well. Like if there was something that you weren't sure about on quiz 1, I want you to walk into the exam being like, I got this. I learned from my mistakes. I figured out what a limit means graphically, and now I know I can do that. Okay, so just because the week is over doesn't mean that learning sort of stops, all right? So I encourage you to sort of take that time to go back over and look at the answer key. But what's new for today? All right, so what's new for today? We're going to take a look at some things that we started to talk about last week. So in particular, we're looking at limits when we get to something called vertical asymptotes. We're going to look at how limits applies to something called end behavior. And all of these are clumped under this category of infinite limits. And by the end of today, the goal is that we have an idea on how to find these infinite limits, both graphically, like from a picture, as well as numerically. All right, so without having a picture, how do we find that limit? All right. So that is where we are headed for today. And so before we jump into that, let's read this little blurb about rational functions. We're going to take a look at this chunk together. Okay. So in pre-calculus, at some point, you learned about something called rational functions. Okay. Now, I know that for some of us, pre-calculus was like a long time ago. Some of it was just last semester. But no matter how recent or how long ago it was, it's entirely possible that you're like, but I don't remember what that is, okay? And so I put together a rational functions review activity on Desmos. but we're not going to do them in small groups. We're going to do them as a whole class together, because I want us to focus less on like, I don't know how to do this question by myself and kind of get stuck, but really think about like, what are hearing like the ways that other people are thinking about these questions, okay? Now, if you happen to have taken Math 116 with me, you can go back to 3.7 part 2 notes, and that will be probably a good refresher on what we're about to talk about, okay? And now let's jump into this activity together. After that, we're going to tie it all into limits. Okay, so we're going back to some old content, and then we're going to come back and look at how it relates to the limits that we've been looking at. Okay, and so let's go ahead and get started. What's the best way to do this? All right, so I'm going to go ahead and stop sharing this screen. Maybe I can just share directly from here. Okay, what do you folks see right now? Do you see the Desmos activity on the screen?
Yes.
Yes, okay, great, thank you. Okay, so let me close out of this for a moment, but if you go into your classes, all right, and again, this one is going to be optional, okay? So rational functions review is optional, all right? We will do this together, whoops, but you will not be expected to turn this in for you. Okay, you can take notes while we're doing this. You can open up your own activity. It is in your Desmos classroom, but you can open it up and sort of type it in yourself for your own record. That's absolutely fine, but we'll just go ahead and do this one together, okay? All right, so here's our first screen on Desmos. This is one of the features that I like about Desmos is we can play sort of a sorting game. We can match things, okay? And so in this case, we're matching the rational function part with how it's found, all right? And so let's see if we can, if I were doing this, I would maybe look for like things that I'm looking for, right? So for example, we see y-intercepts, we see zeros, right? So I can click and drag these different cards. We have holes. We talked about holes in a graph last week. We have vertical asymptotes, and we have end behavior. And looking at this, I probably should have stacked them down the page maybe to give myself a little bit more space, right? So these are all sort of the characteristics of a rational function. Okay, and so now our goal is to match each of these 5 here with a process in this clump of 5 processes that we have here. Okay, and so I'm wondering if anyone can take a look at either the y-intercepts, zeros, holes, vertical asymptotes, or end behavior and tell me which process might be something that we use to answer that particular question. Okay, so Dallas, thank you for being brave and answering that question. So he says a y-intercept means we set the x equal to 0. Okay, and so in general, every y-intercept has an x coordinate of 0, right? So we had like 0, 1, that point would be 1 on the y-axis, right? 0, -5 would be 0, -5 would be -5 on the y-axis, right? So I'm going to take set x to 0 and I'm going to click and drag that one and put it in the same box as x-intercepts, okay, or as y-intercept, okay? And so if you decided that was a mistake, you could sort of unclump them, right? Or you can put them back together like that, right? So that's how the matching parts work. Okay, so I see someone who has talked about end behaviors, right? So I see a message that is end behavior maybe is about comparing degrees of the numerator and denominator. And so I'll go ahead and drag those two together. And so now I can see there's a little arrow on the bottom and they've clicked together. So that's like my way of matching them on Desmos, okay? All right. Anyone have an idea about holes maybe? We talked about holes in a function a lot last week. Canceled factors. Okay, so at some point in our lessons last week, right, we ended up with one factor on the top, one factor on the bottom. That's how we got 0 over 0. And that one does in fact get you the holes. Okay, so we just click and drag that one over and we've matched holes with set canceled factors equal 0. All right, well, we've got two more left. Whoops, we've got zeros and we've got vertical asymptotes. What is a 0? Maybe someone answer that for me first. Depending on your past experiences, we sort of use different languages around what a 0 means, but can anyone tell me in the mathematical context? And I don't mean like the number 0, but what is a 0? Okay, so for those of you who are like, I've never heard of a 0 before, a 0 is a fancy way of saying x-intercept. Okay, a 0 is a fancy way of saying an x-intercept. And so it is in fact that we're going to set the numerator equal to 0, okay? And the vertical asymptotes, and we talked a little bit about this last week, is the vertical asymptotes happen to be the one that there was just the factor on the bottom. And so that's where we set the denominator equal to 0 and we solve for x, okay? And so these right here matching, and I can see at the top it says you are correct. So that means, all right, I've got this correct and now I can move on, okay? Now, if you were doing this on your own and maybe you accidentally matched, two that were wrong, right? So let's say that you said y-intercepts is set numerator equal to 0 and a 0 is where you set x equal to 0, right? There's nothing at the top that says you are correct. So that would be an indicator that there's a mistake somewhere, okay? So let me just fix this. So we've got what we had before, all right? And I'll give you a moment if you want to take a screenshot of this for your own records later, but I would say that these processes, right, the concept and the process, and like knowing which concept means which process is definitely a really important skill that I want us to develop over the semester, okay? So let's go ahead and click next, all right? We're going to click next here, and now we're going to take a look at some pictures. All right, so in this case, we have a picture of a rational function, okay? And so in particular, the rational function part, and let me see if I can sort of draw this. The rational function part is this green branch and this green branch. So those two that I just colored over in the red, those are the rational functions, okay? The question here says, identify the vertical asymptote. Make sure to write it as an equation. So can someone tell me in this picture, where is the vertical asymptote? Okay, and so Dallas says x equals 3, and that looks like this blue line right here is indeed a vertical asymptote, okay? And so I've seen a lot of folks who are like, oh, well, that vertical asymptote is at 3. And they just type in 3, and they hit check, and they don't get anything that says they're correct, okay? One of the things that I want to make sure that we are doing as we explain our mathematics is to make sure we're explaining things clearly. And so part of that means we got to be very precise in our language. We want to say x equals 3, and then we get a big bright yes in red because that is in fact the location of that vertical asymptote. Okay, and so as you're writing answers for quizzes and things like that, you also want to make sure you're communicating to me, I didn't mean just 3, I meant x equals 3. Or I didn't just mean 3, I meant y equals 3, right? So the more clear you can be, the easier it is for a reader to interpret your work, right? Are there any questions about how we knew this is where the vertical asymptote was? All right, let's move on to the next slide. All right, identify the horizontal asymptote. And I'm going to ask us to type our answer into the chat, but don't hit enter yet. All right, so based off of what we did just now with the vertical asymptote, what do you think the horizontal asymptote is going to be? Make sure you write it as an equation. Type that into the chat, but do not hit enter yet. All right, do not hit enter yet, but I will count down in just a little bit, and then we will all chat blast here so that we can see what answers we have. And so in 3, 2, and 1, if you could hit enter. All right, all right. I see a bunch of x equals 3. I see some y equals 3. I see a y equals 4. Okay, I love that we're being really careful about a bunch of things here. One, the units, right? We're counting, each box now is counting by how many? Yeah, each box is counting by 2. Now the horizontal asymptote, what color is that asymptote right now? It's blue, exactly. Now, along this blue line, okay, along this blue line, if we were to, whoa, that's a terrible line, but you get my point. Along this blue line, if I were to pick a point on this line, like let's say here, okay, could someone tell me what the coordinate of that point is? All right, 10,3, I agree with that. Okay, let's say I picked a different point, maybe like right here where that green check mark is. What coordinate would you tell me is at the green check mark? -6, 3. I agree with that. All right. Now, if I were to pick any line on this asymptote or any point on this asymptote, what would they all have in common? Yeah, every single, exactly, Jordan. They would all have the same y value, okay? So because all points on this horizontal line share the same y value, we call the equation of this line y equals 3. Okay, That's supposed to say line, not linear. That's not a new mathematical term. That's a Judy typo, okay? But because all the points on this horizontal line share the same y value, we call the equation on this line y equals 3, okay? So I go ahead and stop annotating. I'm going to type in here and I say y equals 3 and I check my answer. We are correct, okay? All right, so here we have a rational function, right? And so a rational function is exactly something like this, okay? In fact, you typically see a polynomial on the top, a polynomial on the bottom, right? So a rational function is a polynomial divided by another. Right? Now, it does say factor the rational function and then find the different parts. And so I'm wondering right now if we could please factor the numerator, all right? And I'm going to ask you to type the factored version into chat, all right? And again, we'll take maybe about a couple minutes to think about that. And then I'm going to have everyone enter in their factored version into the chat, and then we'll take a look at that. Okay, so in the privacy of your own learning environment, if you could go ahead and factor the numerator. Right, and again, if you could type that into chat, and you can just use parentheses, the letter X for the X's and plus and minus and whatever your numbers are, go ahead and type that into the chat. All right, I see a bunch of ones that are X minus 5 times X plus 3. That is great. Okay, and so it says over here, the first line in this chart, I have function in factored form. And so when I click on this box over here, I'm able to type in my function, okay? So I'm gonna do X plus 3 times X minus 5, right? Now, how do I get to a denominator? Like, how do I make Desmos make a denominator here? Yeah, we're just going to say divide. And as soon as we hit divide, it makes it into a fraction for us. Okay. Now, I did see some folks who had already factored the denominator. So factor the denominator, right? And so if we factor that denominator, we should get X plus 3 times X minus 3. Okay. Now, the only reason I put double parentheses on the top is to make sure that Desmos took the whole numerator and put it on top of the whole denominator, all right? So here's our factored form. Now, based on that, which factor, so listen to that carefully, which, well, not there, which factor helps us find the whole? Right, I see a few folks who are like the X plus 3. I see a few folks who are saying X minus 3. All right. Kelvin, tell me why you say X minus 3. You are the lone voice in the X minus 3 right now. All right, so, okay. So remember, how did we get a whole in, how did we know that we had a whole in the function from last week? Well, we knew there was a whole when we got 0 divided by 0. Okay, that means that there is a whole whenever there is a common factor between the numerator and denominator. Okay, so in that case, in this case, common factor is x plus 3. Okay. Well, what x value makes that 0? In other words, when does x plus 3 equal 0? What x? Yeah, at x equals negative 3. Okay. So over here where it says x value of the whole, we can type x equals. Negative 3. Okay. Now let me pause for a moment. Are there any questions about how we got to that negative 3? All right, so the factor in common, like there's one on the top and one on the bottom, that tells us where the whole is. Okay. Which, that does not say which factor tells us where the vertical asymptote. Good. The factor that is in the denominator. Okay, so it is in the denominator and only in the denominator will tell us where our vertical asymptote is. Okay, so when does x minus 3 equal 0? Well, x must equal 3. Okay, so over here, I'm going to exit out of the annotate. And this is a 3. Okay. All right. Last but not least question on here. Oh, yes. Nora, what's up?
So let's say you have multiple factors in your denominator. Does that mean that you'll have multiple vertical asymptotes?
Exactly. I love this what if question. Let me go to annotate and see if I can. Okay. So if on the bottom, I also had like x plus 1, x plus 2, x plus 17, all in the denominator as well. Okay. Then we would have vertical asymptotes at x equals negative 1, x equals 2, and x equals negative 17. Does that answer your question?
Yes, thank you.
Great. Okay. All right. Now this last question. Where are their horizontal asymptotes? Right? That one, I think, is something that we tend to forget a little bit more. All right. Does anyone happen to remember? How did we know? We know when horizontal.
Is it the x minus 5?
I wish, right? It would be so nice if it was the x minus 5, because everything else we already looked at factors. It is not, unfortunately. Okay, so this is where sometimes math is like a little disappointing. You're like, I really just want it to be the other factor there, but it's not. Okay.
Yeah, I was like, maybe it's just so straightforward that it was x minus 5.
Yeah. But I love that you said that, because I've definitely seen like sort of in a moment of panic, students are like, I don't know, I'm just going to pick the other factor, right? But it is indeed, as Raylene, is that how you say your name?
Yes.
Okay, great. So Raylene has said there's a ratio of leading coefficients, and that is actually exactly what we are looking for. Okay, so we're going to talk about this in a little bit, like we'll actually write it out, like how we find those. But for right now, what is the leading coefficient coefficient for the numerator. Right, that's a lot of vocabulary there, but it is indeed 1 because the leading term is x squared and the coefficient of x squared is 1. Okay, so it's not the degree. It is not the degree. We're looking for the leading coefficient. So like what number is in front of that term? Okay, so what is the leading coefficient for the denominator? Leading coefficient in the denominator. And let me actually go ahead and delete that. Yes, Enrique, you are correct. It is a 1 with an exclamation point, right? It is 1 because the leading term is x squared, again, in the denominator, and the coefficient is perfect. All right, well, ratio, that word that Raylene used, the ratio, means we take the leading coefficient on the top and we divide it by the leading coefficient on the bottom. So 1 divided by 1, not a trick question, gives us 1, right? No matter how we feel about Monday mornings, I hope we can take comfort in the fact that 1 divided by 1 is 1, okay? But be careful here though. If I just type in 1, all right, let's see what we get. Oh, I got a check mark for the -3. The x value of the whole is -3. What do I need to change about how I wrote 3 to get a check mark? Yeah. Any vertical asymptote is written as x equals a number. Okay, so I just wrote 3, but the computer's like, I don't really understand 3. But if you say x equals 3, now we get our check mark. Okay, how do I change the 1? How do I change that 1 to get the check mark? Great, exactly. Nor we're going to say y equals 1. We've got our check mark. And I think maybe this just doesn't want that up there. Okay. All right, so. Yes, go ahead.
So if I had like 16x squared over 8x squared, then my horizontal asymptote would be 2, right?
16x squared divided by
8x squared.
8x squared. Okay.
Yeah, so that would just be 2.
Yes, in that case, the horizontal asymptote would be y equals 2.
Perfect, thank you.
Great. All right, let's clear that out. All right, so consider the following questions. So this is the function we had on the previous slide. And so now I've asked a few what if questions, all right? Nor it's almost like you're reading my mind when you ask these what if I have this, what if I have that questions. Those are exactly the kind of questions that I think when you're studying, asking each other these kinds of questions, it gives you not just one practice problem, but like a bazillion practice problems that are all small changes in the question. And that's really where a lot of these test questions come from, right? Like when we go to a test, chances are we're not going to see the same exact question we saw on a quiz or on a homework or in class, but we might see a variation on it, a twist on it, right? And so when we ask ourselves these what if questions, we're really trying to answer more than one question at the same time. Okay, so in this slide, my question is, what if we want this function to have a vertical asymptote of x equals -2? How do we change our equation to make that happen? All right, so take a moment, think about how would we change this equation? Maybe we'll see if we can annotate right on here to help do that, all right? Hmm. Okay, so if you're saying multiply by x plus 2, are you saying you multiply the whole function by x plus 2?
If you multiply the denominator, don't you have to multiply the numerator, or vice versa?
Okay, so yes and no. If we put an x minus 2, let's just extend this fraction line a little bit. All right, and now if up here I put x plus 2, and down here I also put x plus 2. All right, let's say we just added that on to our equation. Does that give us a a vertical asymptote at x equals -2?
No.
No. Why? That would actually give us a whole, right? We have x plus 2 and x plus 2 on the top and bottom. Okay. Now, normally when we multiply by like the same thing on the top and the bottom, that's because we don't want to change the question. But if we read what this says, it says, how do we change our equation to make this happen? We're allowed to make a different function. Okay, so knowing that we don't have to multiply top and bottom, how would we modify Noor's answer to get a vertical asymptote at x equals -2?
Are we able to change the numbers in the numerator and the denominator?
They don't want to change the numerator.
Yeah, exactly. So if we take this, oops. All right, if we only multiply on the bottom, okay? We only do this, and we make sure there's no x plus 2 on the top, we've guaranteed ourselves a vertical asymptote at x equals -2. Okay, now I see some other answers in here, which are possibly valid, okay, are possibly valid. But we also want to think about like, what's the most efficient way to get there, right? And so like, what do we know about vertical asymptotes? It means there's a factor on the denominator. That factor is only on the denominator, and when we set it equal to 0, we'll get x equals -2, okay? So I would say that the simplest way to do this would be if we just put a 1 over x plus 2, just like Dan has said in the chat, all right? We could also, as Kelvin said, instead of having x minus 3 on the bottom, we could put x plus 2 instead. That would be okay as well. Okay, so I think those are two really great ideas. And let me go ahead and capture those in the in this here. So option 1, we can multiply function by 1 over x plus 2. Or option 2, we can change x minus 3 to x plus 2. So either one of those would be absolutely fine. All right.
How can you just change the x minus 3?
Because we only want to say like, what are we changing about the function? It could be an entirely different function. That's still okay.
Okay, that makes sense.
Okay. All right, so let's try another what if question, right? So here's my function from the previous slide. It's the same function, but now the question is, what if we want this function to have a vertical asymptote of x equals 0? How do we change our equation to make this happen? All right, so everyone take a moment. Think about this. Type your answer in, but don't hit enter yet, okay? What would we change about this to get a vertical asymptote of x equals 0? All right. And when you're ready, go ahead and hit enter for your answer. Great, great. All right, so option, whoa, that is not option. Option one, that also doesn't say option. Option one, all right, I like what Jordan said, multiply by only x on the, let's say, denominator, right? So multiply by only x on the denominator. Okay. Now we don't want to multiply by 0. We don't want to do that. What we're saying is like if I put in x equals, if I put 0 in for x, it will give me undefined. But in general, we're going to leave it as an x, okay? I saw another answer that was exchange x minus 3 for x in denominator, and both of those would work, okay? All right. Looks like we've got about 3 more here. What if question? All right, so what if we want this function to have an end behavior of y equals 2? And so before we talk about this question, end behavior is another way. Nope. Horizontal asymptotes are one way of describing horizontal asymptotes are one way of describing end behavior. What was the horizontal asymptote for this function? Was y equals 1. I agree. The horizontal asymptote was y equals 1. So how can I make the horizontal asymptote y equals 2? Ooh, Stefan, be more specific, because I see more than one x squared. Okay, so let's see if this annotating will still work. If I put it, that is the most unattractive 2 that I've ever written, but if I have a 2x squared in the front and a 1x squared on the bottom, right? And we think about our leading coefficients. The leading coefficient in the numerator is 2. Leading coefficient in the denominator is 1. So ratio is 2 divided by 1, which equals 2. All right, and that is exactly how we can take this function and now give it a different horizontal asymptote. Okay, so we can multiply the numerator by 2. Okay. All right. What if we want this function to have an end behavior of y equals 0? All right, well, I'm going to say that I would suggest you come back and let's think about this again after our lesson today. Okay, so let's come back and think about this question after our lesson today. I bet it's going to make a little bit more sense, but yes, Marilyn is definitely on the right track. Changing the degree of the denominator is going to be really important here. Okay, so great intuition there. And we're also going to leave this for after we finished our lesson today. So what if we want this function to have an end behavior of positive infinity or negative infinity? Okay, so as we go through today's lesson, I want you to keep those questions in mind, like how do we make that happen? Okay, you can go back. You don't have to turn this assignment in for a grade, but you can come back and use this to kind of review the content that we learned today. Okay. And so with that, I'm going to stop sharing this for a moment.
Professor, actually, could you show me the answer for the sixth question? I missed that. Is that something you can do?
Not right now, unfortunately, because it doesn't save on when I'm just doing the student preview.
Oh, okay.
Okay.
Good.
Okay. But you can definitely go and try it on your own. And if you have questions, you can come chat with me in office hours about that. Okay.
Okay. Thank you.
All right. So let me pause this recording. All right. So, so far we've talked about what we know, what's new, rational functions, and that Desmos activity was meant to be a review of content that was learned in pre-calc. Now, I think we're all in different places here. So for some of us, maybe it would be beneficial to go back over that review again on our own time. Maybe it would be helpful to come talk about it in office hours. And so keep in mind when I'm saying this is a good review, it doesn't mean like, well, if you didn't learn it in the past, I don't feel bad for you. It means like it's going to be important, and I'd love to help you make sure you understand that so that the rest of the content also feels good to you. Okay. And so let's take a look at how vertical asymptotes relate to limits. All right. And so we're going to take a look at some graphs here, and we're just going to practice using the limit notation that we used last week. Last week in particular, a lot of times things were pre-filled out for us, and I want to get us practicing how do we write that on our own. Okay. How do we use that proper mathematical notation? So let's start with this graph right here. Can someone tell me where is the vertical asymptote? X equals 0. Lovely. Great. So this in particular right here, okay, has an equation of x equals 0. And so this is our vertical asymptote in the graph. All right. And so if we call this function f of x, just to give it a name, and I were to use limit notation, if I wanted to say, what's happening as we come from the left, I would write the limit as x approaches. What would I write underneath or next to that arrow? What would I write next to x? Okay, I buy it. I would say x is getting close to 0, but that alone wouldn't be enough information, right? We need that little minus sign where there's like an exponent, right? To show us we're coming from the left. We want to say we're looking at the function in the picture. So we got to write the f of x part. And if you were to say, visualize this and you're coming from the left, what y value would you say this function is getting really close to? Yeah, Kelvin, I'll give you the almost on the infinity. In fact, we are going to negative infinity just because the graph is going down, right? And so this right here, as a friendly reminder, just means from the left. Okay. All right, well, as I'm writing this, how could I change this to say from the right? Yeah, instead of that minus sign being minus, I would make it into a plus sign. And so I could say the limit as x approaches 0 plus of this function would equal, let me get that graph back on the picture for us. What would we say that is approaching? Yeah, if we come from the right-hand side this time, it is indeed going up to positive infinity, right? Remember, we're looking at the y value. So what y value is it getting really close to? Positive infinity. Okay. So quick note here, this means from the right. Okay. All right, great. So that's a good way to use our notation to describe what's happening on the graph. Vertical asymptotes in the second graph. I would agree. There are indeed no vertical asymptotes. So we could say that there are no vertical asymptotes. All right, and move on to the third example. Okay.
I'm sorry, Professor. I struggle a lot with like this graph situation.
Okay.
How would you just like determine that there's none?
Okay, so this graph right here is sort of like this, and it sort of keeps going up and out forever here, and like down and out forever here. Okay, and so a vertical asymptote on a picture means like there's actually a value where you can't plug anything into the function. Like if I plugged in a number, I would get undefined out. In fact, if I plugged in 0, I would get undefined out. And so what that looks like on the graph is it's literally missing this whole strip.
Perfect, that makes sense. Thank you so much.
Okay. All right. So let's take a look at this last picture here. Okay. Let's start with a question. Yes, Dallas, we can, but we're looking primarily at vertical asymptotes right now. Yeah. So we could write a bunch of different limits for all of these, but the feature that we're focusing on right now is precisely vertical asymptotes. Okay. So let's start off with this. How many vertical asymptotes do we think there are for this picture? And I'll give us a moment to kind of think about it. But how many do we think we have? And you can go ahead and type a number into the chat. Maybe let's wait. Yep, or not wait. I see a bunch of people who are saying 2s. All right. What is the X value for one of those vertical asymptotes? Yeah, I would agree. We have right here, in fact, a vertical asymptote. And the way I think people saw this is like this part kind of goes up, but then like this part is like going down. So they don't really connect, right? All right. And exactly, Jordan, the second vertical asymptote is actually at x equals -1. All right, so we've got x equals 1, x equals -1 as our equations for the vertical asymptote, right? We want to be really thorough in that notation. And so when we practice writing our limit notation here, we're actually going to have 2 different vertical asymptotes to look at. So let's look at first when x equals -1, and then separately we'll look at x equals +1. Okay. So if I want to write the limit as x is approaching -1 from the left, I want to put another negative sign up there. And let's just for this sake call this function g of x, right? So the limit as we get close to -1 from the left of g of x is all right, so if we come from the left, we're tracing this way, we're tracing, and it sure looks like it's going down to -infinity. Okay. All right, what about the limit as x approaches -1 from the right for g of x? Yeah, so I see a +infinity. All right, so keep in mind, this is the vertical asymptote I'm looking at, and I'm coming from the right, and it's going up to positive infinity. Okay. All right. Here's my left-hand limit for x approaching 1, and my right-hand limit as x approaches 1. And what I'd like us all to do is this. You're going to type in 2 symbols, okay? So if you think this goes to negative infinity, you're going to type in a negative. And if you think this goes to positive infinity, you would type positive. So you would write like negative, positive. Does that make sense? So whatever you think the answers are, don't worry about typing infinity, but if you think it goes up, you're going to type positive. If you think it goes down, you're going to type negative. And you're going to type 2 of them because we want to look at the left-hand limit and the right-hand limit. Okay, so take a moment into typing into the chat. You're going to type in like plus minus, plus plus, minus minus, minus plus, whatever you think it is. And let's hold for a second, just to give everyone enough time to think. All right, that's always the worst when you're like, oh, I'm almost at the answer, and then someone else shouts it out, and you're like, oh, I would have gotten there if you just given me 10 more seconds. All right, and go ahead and hit enter. All right, I see a bunch that are plus minus. I see some that are the same sign and some that are switched. All right, so we're looking at this one right here. And from the left-hand side. So if we look at the left-hand side, we see that it is going up. Okay, so plus for the left-hand limit is correct. And then if we think about the right-hand side, we see that it is going down. So plus minus is indeed the correct answer. All right, so plus infinity minus infinity. Okay. All right, so hopefully that was good practice in like just reviewing what the notation means and how to find things with a graph, right? But we also want to make sure we answer this question, how do we determine limits without a graph, right? That's also important. And so I want to write a few notes for us right here that I think will be helpful, okay? I want to keep in mind that a vertical asymptote happens when factors that are only in the denominator, right? Happens when factors that are only in the denominator are set equal to 0, and we solve for x, all right? So vertical asymptotes happen when factors that are only in the denominator are set equal to 0, and we solve for x. And so if we take a look at this first example here, we have f of x equals 2x squared plus 5x minus 3 over x squared plus x minus 2. And so if we were to factor that, and there is a factoring exercise on Desmos for later this week, but if you're like, oh, factoring has never worked out well for me, this is the time. This is literally the time to embrace it and be like, I'm going to get better at factoring this semester, okay? And so when we factor this, in the numerator, I believe we get 2x minus 1, and we get x plus 3. And in the denominator, we get x minus 1 and x plus 2, okay? Now, after we factor, we should say there are no holes in this function, right? There are no holes. How many vertical asymptotes are there? Great. There are no holes, but there are 2 vertical asymptotes. Can someone give me the equation for one of the vertical asymptotes? Great, I buy that. X equals 1, and the other one, the other equation. Great, X equals -2, right? Now, can I get someone to explain where Jordan got these values from?
He set the
denominator.
denominator equal to 0.
Perfect, perfect, right? We take this denominator, we set each factor equal to 0, we get x equals 1 and x equals -2, okay? Also a great way to study. Someone can help give you an answer, but if you can explain where they got their answer from, you are showing a whole lot of understanding there, okay?
Professor, could I ask too, like when you determine no holes is because the numerator and denominator don't have like items to cancel?
That is exactly why.
Okay. I just want to make sure I like completely understand that part.
Of course. Now, that is something that if I were taking notes, right, I'm taking my own notes and I'm like, oh yeah, that was a really good question. I might go back in and write because there are no common factors for the numerator and denominator, right? Like no holes because of this, but there are 2 vertical asymptotes because we have 2 factors that are only in the denominator, okay? So there might be things that you have in your notes that we don't have in ours, but that's a great thing to do, right? Write those extra explanations for yourself. All right, so we're gonna walk through this example right now together, okay? And we're gonna take a look first at x equals -2. Okay, we're gonna start there. Now, I claim that without having a graph, we can tell whether the function is going to go up on one side to positive infinity or down to negative infinity. All right, and so here's how we can check that out. We're going to start by finding the left-hand limit. Okay, so we're going to take the limit as x approaches -2 from the left. So I want to make sure I have that second little minus sign to show me what's happening when we come from the left. And I'm going to write out the whole function. So 2x minus 1, x plus 3, x minus 1, x plus 2. Okay. Now, what was the first method that I said we should try last week? I was like, try this method before you do anything else.
Plug it in.
Exactly. Substitution, right? We plug it in, we see what happens. But I bet we can tell that if we plugged in -2, we would get a 0 down here, and that would be a problem. But this minus sign actually helps us be a little bit more clever in what we choose. Can someone tell me what is the number that is really close to -2, but a little bit more negative? Okay, so what number is really close to -2, but on the left of negative? All right, I see one vote for -2.1. Anybody have any other ideas? -3, sure. What else? -2.0001. Yep. Okay, so we have a bunch of options here, right? The key word here is really close. In math, when we count 1, 2, 3, 4, 5, right? 1 is kind of close to 2, but you know what's even closer to 2 is like 1.5. Or you know what's even closer to 2 is like 1.9. So when we say really close, we mean, excuse me, really close. And so I would suggest picking negative 2.1, right? Negative 3, even though it seems like it's pretty close to negative 2, is still a little too far away, okay? So we are going to plug in negative 2.1 everywhere we see an X. And don't go rushing for your calculators yet. We're actually going to do this without one. Okay, so we've sub in number close to negative 2 on the left. Okay, oops. Could someone remind me again, why are we plugging in a number that's really close to negative 2 on the left?
As you're approaching,
Yeah.
you're trying to get to the closest.
Exactly. In fact, this part down here tells us what to plug in, right? This, maybe we even circle this, we say this tells us what to sub in. We want to sub in something really close to negative 2, but on the left. All right. And now, let me pause for a moment. Okay. The reason why I said let's not get calculators out is because, weirdly enough, I don't care what number this is. Okay. I don't care what number this is. What I care about is the sign of that number. In other words, in all the pictures that we saw, what's happening around a vertical asymptote? Well, the function is either going up or it's going down. So if I get a positive number out here, it means the function is gonna be going up. If I get a negative value out, it's gonna mean the function is going down. Okay.
That was actually my next question too. I'm like, because what if you pick any of those numbers? It doesn't even matter.
Right, exactly. And that's exactly the case. So let's say we were like, Marilyn said negative 2.1. That seems close enough for us. But then there's some of us who are more in Dallas's camp who are like, I want to get even closer to that asymptote. So I'm going to pick negative 2.0001. And then someone else is like, well, if Dallas is going to do that, I'm going to do negative 2.000000001 and see what I get. But I argue that all of us would end up with the same sign. We would either end up with positive or we would end up negative. The only person who might be out of luck, depending on the graph, is Kelvin. All right. And I say this in a very caring way. I'm not trying to poke fun here, but I'm not joking when we say sometimes 1 is too big of a distance when it comes to graphs that we're looking at. Right. So as close as you can get without driving yourself crazy writing in a number with a bazillion zeros in there, that's kind of as close as you want to get to practice plugging in that number. Okay. And so since we only care about the sign of the number, okay, so we only care about the sign, let's start down here. Negative 2.1 minus 1. Is that going to be a positive value or a negative value?
Negative.
Negative, exactly. Okay, so this is negative. All right, someone else tell me about this second parentheses down here. Is this going to be positive or negative?
Still negative.
Great. All right, so we've got 2 negatives down here. All right, Let's take a look at this one right here, this factor, negative 2.1 plus 3, positive or negative? That is indeed going to be positive, all right? And last but not least, I just thought this one was a little bit scarier to start with, but is that going to be positive or negative? Great, yeah, I agree, okay? So all we've done is just check the signs, all right? So like this, we knew was negative. Let's pick a better color. This, we knew was positive. This, we knew was negative. And this, we knew was negative, okay? All right. Someone walks up to you on the street, tells you you have a negative times a positive, and you tell them that that number will be
Negative.
great. And someone else walks up to you on this very strange mathematical street. They're like, but okay, now I got two negative numbers. When I multiply those, I get
Positive.
great. And then a third person is like, okay, but what happens when you divide those two? I think we can all agree we would end up with negative. Okay. All right. But all of this is to help us imagine, is it going to positive infinity or is it going to negative infinity? So if you leave your answer like this, I would say that's close, but it's not answering the question. How would I answer this question fully? Yeah, I would say that this limit is indeed negative infinity, right? Meaning if I graphed this function and I looked at negative 2 x value, on the left, the graph would be going down. Okay. Nora, I see you have a question.
Yeah, so just by looking at the equation, how can you even tell that it's going to be infinity? Like I know how you can say, oh, it's going to be in the negative, but how do you know infinity?
Okay, so keep in mind, we already knew going in that this is a vertical asymptote, right? We knew this was a vertical asymptote. Well, the only things that can happen around a vertical asymptote, if you have a vertical asymptote, the function's either going to go up or it's going to go down. Those are literally your only two options.
But what if you had like a horizontal asymptote, like at the bottom, like, you know what I mean? So if you had a horizontal asymptote, couldn't that stop the infinity? Yeah.
But we're looking at a vertical asymptote.
Okay, got it.
Okay, we're looking at a vertical asymptote right now. So I think I understand what you're asking. Let me answer that when we get to the horizontal asymptote part though. Okay. All right, let's try the similar process for the right-hand side of this vertical asymptote. Okay. So I write the same thing, the limit as we approach -2, but with a plus sign, because I want to say I'm coming from the right this time. And I plug in my function. What would be a good value to sub in for x? All right, I see Dallas has said -1.9. What would be an even more Dallas answer than that? Last time he said -2.0001. If someone were to up Dallas, what would you put in as another number? Yeah, right, we could put in -1.9999. That's even closer to -2, right? But since we're only caring about the sign, because our only two options are positive or negative, right? Let's choose the less Dallas version that requires less writing, so we can just focus on the sign. Okay, So we'll get 2 times negative 1.9 minus 1, negative 1.9 plus 3, negative 1.9 minus 1, negative 1.9 plus 2. All right.
Professor, can I ask a question?
Absolutely.
The negative 1.9, can we just keep it the same as like negative 2.1 if we're just worried about the sign? Or it won't work in that situation? Because we're coming from the right.
Yeah, so we have to pick a different number.
Okay, I think I just answered my own question actually in my head.
Yeah.
Sorry.
So negative numbers are hard. I buy that. Negative numbers are hard. If we were to put this on a number line real quick, we have negative 2 here, right? Negative 2.1 is on the left and
Right,
negative 2.9 is on the right. Yeah.
My bad. Yeah.
No worries, no worries. Yeah, I feel like many mathematicians are actually notoriously bad on like left and right and like arithmetic sort of situation. So it's totally understandable. All right, so let's go through these again. And maybe everyone can sort of pick a different one. So if you do the purple one, you think that's positive, just say like purple plus, type that into the chat. You know, or you could say like green plus, whatever you think each one ends up being. And hopefully between the whole class, we can find, oops, all 4 of these. Divide and conquer that labor, right? So what do you think each of those colors will output as far as a sign goes? Okay. All right. Anybody agree with the purple being a minus? I agree that the green is a plus. Yeah, the purple one is just a lot going on. This is going to be a negative number, and then we subtract another negative. So we're going to end up with an even more negative answer there. Great. And the gray one, I have negative 1.19 minus 1 gets me to more minus. Okay, so yeah, Jordan, I agree with you. We have a minus plus times a minus plus, which gives us a plus, or minus over minus, which gives us plus infinity. Okay. The reason why the plus means plus infinity is because there's only 2 options of what happens around a vertical asymptote. Either it's going to go up or it's going to go down. That's it. Okay. Now, for the sake of time, I'm going to suggest as a good exercise for you to try something similar with x equals 1. It'll be a little bit more straightforward because we are looking at a positive number instead of a negative number, but I would later on go ahead and try what this might look like for a left-hand limit and a right-hand limit. Okay.
Wait, Professor, I have a question.
Yes, what's up?
Or just really quickly, can you repeat why we just did this? Like,
Sure. Okay, so if we look at this graph right here, right? We said earlier there's a vertical asymptote at x equals 0. But when we talk about what's happening around it, on one side it went up, but on the other side it went down. But we might have a different graph where maybe like, here's our vertical asymptote, and on one side it goes up, and on the other side it also goes up like that, right? So what we're doing algebraically is we're saying, here is where the asymptote is. Now, tell me, on the left-hand side, is it going up or down? And on the right side, is it going up or down? Okay. So when we think about what's happening around a vertical asymptote, it either goes down to negative infinity or it goes up to positive infinity. Those are our only 2 choices if it's a vertical asymptote.
Okay.
Okay.
Yeah, thank you.
So yeah, and I think these are really good questions that folks are asking. And I want to say this is probably one of the biggest learning pieces about calculus is no matter how good or not good you think you are at math, calculus takes some time to like marinate in your brain. And the more space you can make for that and be like, wait, why is this happening again? The more successful you're going to be overall. Okay, so these are exactly the right questions to ask. But since we know we have the vertical asymptote and our two choices are only positive infinity or negative infinity, we sort of shortcut our substitution by cleverly picking a number that is close to the one we want, but on the side that we want. And then that will tell us if it's going up or down. Okay, that's sort of the end gist of what we're doing here. Okay. Remember, for the ones that are on your own time, you can always ask about those in office hours. You can ask about them during tutoring. You can send me a message on Discord and be like, hey, I did this problem. Here's my work. Does it look correct? I can do that too. All right. So lots of options. It, on your own time does not mean go home and learn by yourself and that's it. And I don't care about your learning. It means I'd love to continue this conversation at a different time when you've had a chance to kind of try it out. Okay. All right. So the second piece to that Desmos activity about rational functions was end behavior. And I think in the Desmos activity earlier, I had said that end behavior includes horizontal asymptotes and what we call other behaviors. Okay, so end behavior includes horizontal asymptotes and other behaviors. Okay. One more thing I want to say about end behavior. End behavior refers to the ends of the x-axis. Okay. We're looking at the ends of the x-axis. Can someone tell me what is the x value at the very left end of the x-axis? We're walking along that x-axis and I get all the way to the left end, yeah, it's going to be negative infinity, right? And I would say technically, yeah, does not exist because we can't ever get to the end of it, but it would go towards negative infinity. All right, what happens if I walk all the way to the right of the x-axis? What x value does that get close to? Yeah, it gets positive. It gets close to positive. All right, nor you were asking exactly the right question. I intentionally did not say that yet, but we are going to answer that question. Okay. All right, so let's go back. Let's revisit. What does it mean to write limit notation? All right, so if I want to say the limit as x approaches the left end of this graph, right? And let's call this function f of x. If I were to trace this picture all the way to the left, what y value would we get really close to?
Sorry, can you repeat that?
Sure. If we were to take this graph and we were to go all the way to the left, what y value would we get really close to? Yeah, we would get close to a y value of 0. Let me zoom in on this graph for a moment. So I'm tracing this, I'm tracing. This is getting really close to the x-axis, right? It's getting really close to this y value of 0. And so when we answer this question, we would want to say that it's getting really close to 0. Okay. And in fact, this negative infinity means the left end of x. Right? Well, it's not too hard to ask the same question, but for the right end, I would say the limit as x approaches positive infinity of this function. And this would refer to the right end of the x. Right? And based on this picture, what y value would we say that's getting close to on the right end? Right? So if we were to trace this out, y value gets really close to that x-axis, and that we know is a y value of 0. Okay. Now, I'm going to shrink these just a little bit because I realize there's something else I want to write here. Right? So one of the rules that you may have learned in pre-calculus, right? And this was something I want to say it was Marilyn who had said this earlier. It might not have been, but somebody earlier said, well, I think it has to do with something about the degrees, okay? In fact, one of the things you probably learned is if you take the degree of a numerator, right? If you have an equation, that is, you take a degree of the numerator, and if you find that that's less than the degree of the denominator, okay? So every time that you look at the degrees and the degree of the numerator is less than the degree of the denominator, that means you're going to have an end behavior of y equals 0. Okay, so in this case, and this is to Nora's question, this is an example of an end behavior that is a horizontal asymptote. Okay. Now, I made these graphs, so I happen to know the equations of them, all right? But you may also know these from your previous math experiences. But this graph happens to have this equation. One over x. Okay. What is the degree of the numerator here? Yeah, the degree here is not 1, because the 1 secretly is describing some power of x. It's not -1. 1 is secretly, saying 1 times x to the 0, right? Anytime we have a constant, like 1, 2, pi, whatever, and there's no variable, it really means x to the 0 or y to the 0 or whatever variable we're using, okay? But what's the power in the denominator? What's the degree of the denominator? 1, great, all right? So in this case, we have a degree of the numerator is 0, and the degree of the denominator is 1. 0 is definitely less than 1 And as one of your peers has referred to this as bottom heavy, okay? It is indeed, the degrees on the bottom are much larger than the degrees on the top. That's going to give you a horizontal asymptote of y equals 0 every single time, okay? But we can always look at pictures and help us figure out what's happening there, right? So before we get to what we do without a picture, let's continue to talk about what we have if we have a picture. So the limit as x approaches negative infinity, let's call this one h of x, equals, and then I'll go ahead and write in this one, the limit as x approaches positive infinity of h of x. Great. All right. I'm going to ask you the same questions I asked you about the first graph. I have this picture. I go all the way to the left. What y value is that graph going to get really close to?
I'm just gonna guess here, -2. Because this is the part that I don't understand, like with reading the graph. Like, do you stop at the -2 or do you just keep going?
Okay, so I'm going to trace the graph towards this end, right? The negative infinity end. So I can start wherever I want. I'm tracing, it goes down, it goes up. And then as I keep going to the left, it keeps going down.
Okay, you just answered my question. Thank you.
Yeah. Okay. So it's going to go to a y value of negative infinity. All right. Okay. Well, let's use the same reasoning. Look at this graph and see what happens if we trace it all the way out to the right. What y value does it get close to if we go all the way out to the right? X value, not an X value, we want the Y value. What Y value does this graph get really close to as we go all the way out to the right? Exactly. We're going to see this function will continue to go up, 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 up forever. That means that at the right end, we are getting to a value of positive infinity. Okay. Now, again, I typed these into here to get the graphs. So I vaguely know what the equation is. This one is some sort of x cubed plus some other things, and then maybe like a -2 situation, okay? What's the numerator of this function? What's the denominator?
Since they're both going to a positive or negative infinity, is it just infinity?
So I don't think I asked my question very clearly. I was asking like what the denominator of the function is. And so the denominator, we can always make anything into a fraction if we divide it by 1, right? So like all of our rational functions have a numerator and a denominator, right? So if we're going to be comparing the degrees here, we want to make sure we can see what the denominator is and what the numerator is, okay? But now if we look at this, can someone tell me what is the degree of the denominator?
0.
Right, because we secretly have that x to the 0. What's the degree of the numerator? Yeah, it's going to be 3, okay? So it turns out that if we have the degree of the numerator and it is bigger than the degree of the denominator, okay? This is when to answer Nora's question, this is when you have those other behaviors. So we end up with no horizontal asymptote. Okay, so if we are top heavy, okay, the degree on the top is overpowering the degree on the bottom, we end up with no horizontal asymptote. Okay. All right. Nora asks a great question. How do you find the degrees?
Huh? The onion fell out of your.
All right. So how do we find the degrees? We look at the leading coefficient or the leading term. Whatever the leading term is, that will tell us what the degrees are. Okay, so like in this up here, I have an x cubed with a bunch of other things, but what's the highest degree? 3. So that's going to be the degree. Does that make sense, Nora?
So how did you find the degree though by looking at it? How did you know x cubed?
Oh, because I made the graph. Like I made it to be that way.
But like, okay, so let's say we were just looking at a graph. How would we know like, okay, this graph is to the second power, third power, fourth power?
That's a great question that I would love to answer during office hours. But keep in mind, we're using pictures to help us figure out what to do without pictures.
Okay, that makes sense.
Okay. Okay. Great. Let's take a look at this last picture right here. Okay. And I'm going to go ahead and write out the limit as x approaches the left-hand side of the graph. We're at negative infinity. And we'll call this one g of x. All right. And then we'll also take a look at what's happening on the right end. And so if you can look at this graph and tell me what's happening to as the graph, like what y value does the graph get really close to when we trace it all the way out to the left? Yeah, it's getting close to that y value of 2, right? It flattens out and the y value there is 2. Now, I know last week when we were just looking at limits for the first time, we made a big deal about how this answer is the y value. We got to keep remembering that, okay? Otherwise, I think it gets very hard to read the graphs. But I would agree that the left end rather gets to a value of 2. What does the right end of the graph get to? It also goes to 2. Okay. So when we look at a graph where the 2 values are the same, but they're not at 0, what that actually tells us is that the degree of the numerator is equal to the degree of the denominator. And anytime this happens, we end up with a horizontal asymptote at y equals the ratio of the leading coefficients. That's a lot of words, but think back to that Desmos activity that we did earlier. We had something that looked like x squared plus some other stuff over x squared minus 9. And while we were doing that, I said, hey, what's that leading coefficient? What's this leading coefficient? And then when we looked at the graph, it gave us a horizontal asymptote of 1 divided by 1. Okay, so this last case if we were to have seen an equation, if we go back and look at that equation, in fact, we would notice that the degree of the numerator and degree of the denominator are equal to each other. In this case, in particular, they're both to the second power. Okay. So 3 pictures to kind of look at, but the bigger question at the end of the day is, okay, so if we can do it with a graph, how do we do it without a graph? Or maybe the other way around, if we have an equation, what does our answer mean on a graph, right? And so let's go ahead and take a look at these examples. All right, so we've got about 3 examples right here. Okay. And let's start by taking a look at the degrees, okay? So can someone tell me what the degree of the numerator is for this function f of x?
4.
Great, and how did you know that?
It's the leading power of the top.
Perfect, all right, I agree. We've got a degree 4. Great. What is the degree of the denominator?
The same.
Ah. Why is it 4? That doesn't look like the leading term. Like it's not in the front.
Well, 7 does have one, but it's x to the power of 0. That's not the highest.
Great, exactly, right? This is the most classic trick in the book. Someone is trying to get you to read too quickly and not realize this really means this. Okay, so I would agree. We are all too clever for that trick. The degree of the numerator is 4, the degree of the denominator is 4. Great. What does that mean we should see on our graph? So since degrees are equal, what does that mean? Do we have a horizontal asymptote, or is it that other behavior? Yeah. We have a horizontal asymptote. Okay, and now if we want to find it, we just take the ratios. So y equals, all right, what number should I put on the top? Great, I agree. And what number should I put in the denominator? Whew, I love it. We are almost 2.5 hours into class, and we did not miss the fact that there is secretly a negative sign in front of there. And not even secretly, they're just hoping that you don't even look at it. -5 is that leading coefficient, okay? So we could write this as -2/5, right? Or we could write this negative on the top over 5. All of these mean the same thing, right? But how does this tie into limits? Well, I could ask you this question in a different way. I could say the limit as x approaches -infinity of f of x, and you would say, oh, that's -2/5, because you knew that the degrees are this equal, you have a horizontal asymptote, and you find that ratio. Okay, so this question is asking the same thing as find the horizontal asymptote, which is also the same as saying what happens when we go to the right end. Okay, all 3 of those are equivalent. All right, let's take a look at example 4. What do we think about the degrees? For the sake of time, I'm going to cheat a little bit and copy paste, and then we can delete and rewrite what we need to. All right, but let's see, what do we get for the degrees? Oh, no, sorry, what's up?
So my question is, you know how you said the limit of x going to negative infinity? It's the same question, like that's what it equals when you find the horizontal asymptote. But is it the same for vertical asymptotes? Is it asking the same thing?
No.
So how do those two, like, how does vertical asymptotes tie into limits then?
Well, I would say, again, that is maybe a question that if you look back, like how do I know here that I'm asking for a horizontal asymptote? Because there's one thing in particular that is a clue that I should be looking at end behavior here.
Oh, is it because the x is infinity?
Yeah, the x is going to infinity, right? So I'm saying go all the way to x equals infinity. But if I scroll back up for a second, right? What is x going to here?
Oh, okay, that makes a lot of sense. Got it.
Right. So it's asking you, hey, do you know there's a vertical asymptote here? Because if you know there's one, then you do all this stuff, right? And so I think this is the phrase, the devil is in the details, all right? So it is exactly that little thing under the limit that tells you, okay, this is what I'm supposed to plug in, or this is what I'm looking for. All right, so I'm so glad you asked that question. I'm sure a lot of us have also been asking the same thing, like, how do we know which one is which, right? And so that'll be a great thing for you to practice on the quiz and maybe do some extra practice problems too, like how do we know what that question is asking, okay?
Yeah, that was a good question because I had the same question too.
Hey, I love this. I am so excited to be back in person with you folks, by the way, and not back with you in person because I've never been with you in person, but I'm really excited. Like, I love the energy of this class. I think there's a lot of really great thoughts happening and people are asking like the juiciest questions. So this is all really good. Okay. All right. Tell me about the degrees. What do we have for the degree of the numerator, for example, 4?
6.
Bingo. Degree of the denominator?
3.
Yeah. All right. So we might need to modify our statement now, right? That our degrees since the degree of the numerator is greater than the degree of the denominator, we have, and I'll give you a moment to look back at your notes, which case is this? Are we gonna have a y equals 0? Are we gonna use the ratio? Are we gonna have a different end behavior? Exactly. Now, I'm not sure if, I mean, this is going to get recorded anyway. I'm not sure that it's okay for me to have top heavy written down in the notes, but I would agree that's a really great way of looking at it, right? If the degrees are larger on the top, they're going to overpower that. So we end up, we have no horizontal asymptotes. No horizontal asymptotes. How could we figure out whether it's going up or down? Anybody have any ideas? How could I figure out whether this is going to be positive infinity or negative infinity? Okay, plug in a close value from the left. All right, what value are we trying to get close to? What x value are we trying to get really close to here? Yeah, we're trying to get to infinity here, and here we're getting to negative infinity. okay? So let me ask you something. Let's just look at 4x squared plus x to the 6th, okay? If I had infinity to the 6th, let's say I had 1,000,000, x was 1,000,000, and I raised it to the 6th power. That's a pretty big number, right? Having x to a power of 6 when x is really big is kind of like saying, oh, you won like the lottery. And let's say you win the lottery and then someone is like, oh, I owe you like $100. Something, it's like a significant amount of money, but it's less than your multi-million-dollar lotto winning. Does that $100 really matter that much to you? If you have like 5.7 billion. Yeah, I mean, sure, an extra $100 is nice, but like maybe it's more important if you only have $100, and maybe it's a little less important if you have like 5.7 billion, right? So when we think about powers, things that are happening towards the end, the important thing here is really the x to the 6th part. Okay. Same thing down here. I have a really big number, and I'm going to do 1 minus that really big number. The 1 isn't going to really make a difference. Rather, it's just going to be this part that's important. Right? So you'll kind of see this strategy in some of the other videos or resources that are out there on the internet. Sometimes people are like, this matters more when we have really big values, and this matters less. And so they almost simplify this problem, and they end up with this is about the same as a negative x cubed graph. Okay. Now, I know there was a question earlier about like, how do you know what graphs look like? But if you happen to know what your graphs look like, this would be another way to help you answer the question about whether it's going up or down. Okay. It turns out in this case that we get negative infinity. It turns out in this case, we get positive infinity. But you can always plug in the idea of negative infinity and see sort of like what matters and what goes away. All right. Now we are just about out of time, but I would say go back over this example 5. Make sure you understand like how to find the degrees, how to figure out whether or not it is kind of like a falling snake. What are the degrees and how does that imply what kind of end behavior there is, okay? And for those of you who were like, I don't really know how to explain my thinking, and I lost a lot of points on this quiz 1 because I didn't explain my thinking, I write out these sentences a lot, not because I like to write them. I would rather write less than more, but I know that in the context of all of us learning together, having an example of a sentence to sort of like copy and paste from is really useful when we're learning how to explain our math, okay? So go back into the notes, read the things we wrote, and then sort of modify that if you're having questions on like, how do you explain your thinking, okay? The very last thing I want to say, because I'm already out of time, is this is a greater explanation for sort of what we're looking at if you want just sort of like a one-piece summary for how we're looking for the different degrees and whether that means you have a horizontal asymptote or not, okay? And that, my friends, is it for today. There will be office hours this week on Wednesday from 8:30 to 9:30. All right, please feel free to pop in if there are like 15 of you who show up at 9:25 and you all want to talk one-on-one with me. That might be a little challenging, but if you sort of, you know, get up a little bit earlier, maybe 20 minutes earlier and pop in earlier, we can always have a more one-on-one conversation if you want, okay? But I would encourage you to look over the assignments that have been graded so far. Think about like what questions you have on the content, but maybe also what questions you have on like the grading structure, like how can you be successful? Like if you are not getting a grade that you want, how can you work to be more successful? I would love to help you with that process, right? I'm not here to be like, like if you didn't do well, I'm just judging you. It's more like if you didn't do as well as you wanted, I want to help you understand how to be better, okay? So that is it for me today. I'm going to stop this recording.